students. First of all, I welcome you all to my third video on the chapter surface chemistry. In the previous two videos, we completed the discussion on adsorption, the phenomenon of adsorption, right? In the today's video, we'll start one more important concept under surface chemistry. It will be catalysis. You come across varieties of chemical reactions in chemistry, right? And these chemical reactions are taking place under particular set of conditions. Chemical reactions are taking place under particular set of conditions. And as far as one example for that, if I consider the chemical reaction, that is decomposition of potassium chlorate. When potassium chlorate decomposes, right, it leads to the formation of potassium chloride and oxygen there. This is one chemical reaction. And this chemical reaction takes place at a temperature of 653 to 873 kelvins. Under this particular temperature, decomposition of potassium chlorate takes place to form potassium chloride and oxygen. Of course, you can balance it by multiplying this KClO3 by 2. Therefore, it will be 2 KCl. Number of oxygen atom is 6. It will be 3O2. This is one chemical reaction where potassium chlorate decomposes to liberate oxygen gas at about 653 kelvins to 873 kelvins temperature. Under this particular set of conditions, decomposition of potassium chlorate takes place, is it not? If same reaction is carried out in presence of a substance called manganese oxide, the same reaction, decomposition of potassium chlorate, is carried out in presence of manganese oxide, the reaction takes place readily but at lower temperature at about, yes, it is 473 kelvins to, yes, it is 633 kelvins. Just observe the difference in the reaction conditions. If the decomposition of potassium chlorate is carried out in the absence of manganese oxide, we need a temperature of 653 to 873 kelvins. That is, we need high temperature for decomposition of potassium chlorate. If the same reaction is carried out in presence of manganese oxide, you will need a low temperature. That means decomposition of potassium chlorate takes place at lower temperature. It means that, the presence of manganese oxide has accelerated the speed of conversion of potassium chlorate into oxygen. Or you can say, in presence of manganese oxide, the speed of decomposition of potassium chlorate has increased. That means change in reaction conditions, they are going to affect the rate of chemical reactions. For the first time, the scientist Berzelius studied the effect of such type of foreign substances on the rate of chemical reactions, and these substances, which accelerate the rate of chemical reactions, he called them as catalysts. For the first time, the effect of the foreign substances on rate of chemical reactions was studied by the scientist Berzelius, and he called those substances, which accelerate the rate of conversion of reactants into products as catalyst. And that is, for the first time, the term catalyst was coined by Berzelius. So, in this particular reaction, manganese oxide acts as a catalyst because manganese oxide, in presence of manganese oxide, rate of decomposition of potassium chlorate increased. Because of that, manganese oxide can be taken as catalyst for the decomposition of potassium chlorate into potassium chloride and oxygen. And therefore, now at this moment, catalyst can be defined as the substance that accelerates rate of chemical reactions without undergoing any change in its composition and mass at the end of chemical reaction is called catalyst. And the phenomenon is called as catalysis. In this particular example, manganese oxide is a catalyst. In presence of manganese oxide, rate of decomposition of potassium chlorate increased. Or you can say, in presence of manganese oxide, speed of conversion of potassium chlorate into potassium chloride and oxygen increased. And therefore, manganese oxide is a catalyst. At the same time, even after the completion of chemical reaction, even after the completion of chemical reaction, the composition of manganese oxide remains same. Before that chemical reaction, composition of manganese oxide was MnO2. Even after the completion of chemical reaction, the composition of manganese oxide remains as MnO2. At the same time, the mass of manganese oxide remains same during the chemical reaction, and that's why manganese oxide is a catalyst. So therefore, catalyst is a substance that accelerates the rate of chemical reactions without undergoing any change in its composition and mass at the end of the chemical reaction. That is called as catalyst, and the phenomenon is called as catalysis. But of course, as far as catalysts are concerned, the activity of catalyst can be increased in presence of certain substances. We call them as promoters. At the same time, activity of catalyst can be decreased in presence of one more kind of substances called poisons. Now let us see, that is catalytic promoters and catalytic poisons. We'll see that. That is the catalytic promoters and catalytic poisons, right? As far as catalytic promoters are concerned, these are the substances which increase activity of catalyst. They are called as catalytic promoters. For example, you studied in the manufacture of ammonia by Haber's process. Look at this. The reaction between nitrogen and hydrogen is catalyzed by, yes, it is that is finely divided iron catalyst, and that leads to the formation of, yes, it is ammonia gas, right? The activity of this iron catalyst can be increased in presence of one more substance called molybdenum. So molybdenum is a promoter that increases activity of iron catalyst. So this is what we call it as example for the catalytic promoter. Yes, the example for the catalytic promoter is molybdenum in the manufacture of ammonia by Haber's process, where molybdenum increases activity of, yes, it is iron catalyst. That is molybdenum. Observe this spelling there. Yes, molybdenum is a promoter that increases activity of iron catalyst. And at the same time, as far as the catalytic poisons are concerned, catalytic poisons are the substances which decrease the activity of catalyst. For example, in the manufacture of sulfuric acid by contact process, we have a key reaction, that is conversion of sulfur dioxide into, yes, it is sulfur dioxide. And in this particular reaction, we use the platinum catalyst. That is, the catalytic activity of platinum can be decreased in presence of a catalytic poison, that is arsenic oxide. As2O3 is a catalytic poison that decreases the activity of platinum catalyst in the manufacture of sulfuric acid by contact process. In the same manner, in the manufacture of ammonia by Haber's process, the activity of iron catalyst can be decreased in presence of hydrogen sulfide. Therefore, hydrogen sulfide is a catalytic poison for iron catalyst. Like that, there are some substances which increase activity of catalyst. We call them as catalytic promoters. At the same time, there are some substances, which decrease activity of catalyst. We call them as catalytic poisons. Here, in the case of manufacture of sulfuric acid by contact process, that arsenic oxide is a catalytic poison that decreases activity of platinum catalyst. Whereas in the case of Haber's process, the activity of iron catalyst will be decreased in presence of hydrogen sulfide. Here, in the manufacture of ammonia by Haber's process, activity of iron is increased by molybdenum there. So this is what we call it as the catalytic promoters and catalytic poisons. Now at this moment, we'll go for the next discussion, that is classification of catalysis depending upon the physical states of reactants and catalysts. The catalysis can be classified into two types based on the physical states of reactants and catalysts, and that will be, yes, it is homogeneous catalysis. Another is heterogeneous catalysis. This is the classification of catalysis. Catalytic reactions can be classified into two types: homogeneous catalysis and heterogeneous catalysis. In the case of homogeneous catalysis, that is the reactants and catalysts are in same phase. The catalytic reactions in which reactants and catalysts will be in same phase. So such type of catalytic reactions are called as homogeneous catalysis. Okay, na? Or you can say the catalysis in which physical states of reactants and catalysts will be same. And of course, such type of catalysis we call it as homogeneous catalysis. For example, in the manufacture of sulfuric acid by Chambers process, the key reaction is conversion of sulfur dioxide into sulfur trioxide. And of course, this particular reaction is carried out in presence of a catalyst, that is nitric oxide. Just observe, this is homogeneous catalysis because reactants are in gas phase, nitric oxide is also in a gas phase. Because of that, this is an example for homogeneous catalysis. Apart from that, in the hydrolysis of methyl acetate, look at this, methyl acetate is a liquid. Hydrolysis can be carried out using water, that's also in a liquid state. And of course, reaction is carried out in presence of catalyst, that is dilute hydrochloric acid, that's also a liquid. That results in the formation of acetic acid, and of course, that is in aqueous medium, that's also a liquid. And of course, along with the formation of methyl alcohol, and that's also in a liquid state, that is aqueous solution. This is another example where reactants and catalysts will be in same phase. Here, this reaction is catalyzed by H plus ions produced by HCl solution, which is in liquid state. Reactants are also in liquid state. That's why, here also, reactants and catalysts will be in same phase. That's why it is an example for homogeneous catalysis. Apart from that, if I take, hydrolysis of sucrose there, hydrolysis of sucrose, this is sucrose, C12, H22O11. And of course, this is aqueous solution of sucrose, which is in liquid state. And of course, hydrolysis is carried out in presence of water, that is in liquid state. And the reaction is catalyzed by, dilute H2SO4 solution. That is, the catalyst for the reaction is H plus ions. Dilute H2SO4, that's also in liquid state. That leads to the formation of glucose, C6H12O6. This is an aqueous solution. And of course, fructose, that is C6H12O6. That's also aqueous solution. That's why the hydrolysis of sucrose in presence of dilute sulfuric acid is also an example for homogeneous catalysis. Here, reactants, they are in liquid state. Catalyst is also in liquid state. And of course, this reaction is catalyzed by H plus ions produced by dilute sulfuric acid, which is in liquid state. And of course, here also, in this hydrolysis of methyl acetate, this reaction is catalyzed by H plus ions produced by dilute HCl. And of course, that is what we call it as homogeneous catalysis. Homogeneous catalysis is a catalysis where reactants and catalysts are in same phase. The catalytic reactions in which the physical states of reactants and catalysts will be same. So that is what we call it as homogeneous catalysis. Apart from that, we have one more kind of catalysis. We call it as the heterogeneous catalysis, right? Look at this. That is heterogeneous catalysis. In the case of heterogeneous catalysis, that is, reactants and catalysts will be in different phases. The catalytic reactions in which reactants and catalysts will be in different phases. The physical states of reactants and catalysts will be different. Such type of catalytic reactions are called as heterogeneous catalysis. Or you can say, for example, in the manufacture of sulfuric acid by contact process, look at this, the manufacture of sulfuric acid by contact process, where the key reaction is conversion of sulfur dioxide into sulfur trioxide. And this reaction is catalyzed by platinum catalyst. Platinum catalyst is in a solid state where reactants are in gaseous phase. Here, the physical states of reactants and catalysts will be different. Therefore, it's an example for heterogeneous catalysis. And of course, this is the contact process. Just observe, in contact process and Chambers process, the key reaction is same for the manufacture of sulfuric acid, but in contact process, we use platinum as a catalyst. In Chambers process, we use nitric oxide gas as a catalyst. That's why the key reaction in the manufacture of sulfuric acid by Chambers process is an example for homogeneous catalysis. This is a key reaction for the manufacture of sulfuric acid by contact process. It's an example for heterogeneous catalysis. Reaction is same, but the catalysts are different. Hagagi. So this is what we call example for heterogeneous catalysis, where platinum is a catalyst. No doubt in your P block elements chapter, we used vanadium pentoxide catalyst, but before that, we were using platinum catalyst. Nowadays, the platinum is replaced by vanadium pentoxide. Hagagi, I'm using platinum here. You can go for platinum also, right? Apart from that, in the manufacture of ammonia by Haber's process, look at this. Here, the reactants are nitrogen and hydrogen gases, and the reaction is catalyzed by iron, solid iron. The reaction is catalyzed by solid iron, finely divided iron, iron powder we are using. Your reactants are in gas phase, catalyst is in solid phase. That leads to the formation of ammonia gas. This is one more example for heterogeneous catalysis. Or you can say, in the manufacture of nitric acid, we have the reaction between ammonia and of course oxygen gas. That leads to the formation of, yes, it is nitric oxide gas, and of course along with the formation of water there. And of course this is one more example for heterogeneous catalysis. This reaction is catalyzed by, yes, it is platinum, which is in solid state. Platinum rhodium catalyst. Platinum is in a solid state, and of course reactants are in gas phase. So this is an example for heterogeneous catalysis. Apart from that, that is hydrogenation of vegetable oils. Vegetable oils, they are in liquid state, and hydrogen is in gas phase. And the reaction is carried out in presence of nickel catalyst, that is in solid state. Look at this. Reactant, vegetable oil, is in liquid state. Hydrogen in gaseous phase. Nickel is in solid state. That is, there is a difference in physical states of reactants and catalysts that leads to the formation of vegetable ghee. So that is what we call it as vanaspati, we call it as, is it not? That is, hydrogenation of vegetable oils leads to the formation of vegetable ghee in presence of nickel catalyst. That generally we call it as dalda, like that, is it not? That is the hydrogenation of oils. So these are all the examples for, yes, it is heterogeneous catalysis. So this is what we call it as classification of catalysis based on physical states of reactants and catalysts. Okay, now? So we'll see next topic. Yes. Now at this moment, as per your NCERT textbook, we are supposed to discuss theories of heterogeneous catalysis. We are supposed to discuss the theories of heterogeneous catalysis. We'll see that the theories of heterogeneous catalysis. Theories of heterogeneous catalysis. Here, under this particular discussion, we are going to something about the reasons why the presence of catalyst is going to increase rate of chemical reaction. In order to understand that mechanism involved in increasing rate of chemical reactions in presence of catalyst, we can make use of certain theories. As far as the theories of heterogeneous catalysis are concerned, we have one theory, that is what we call it as adsorption theory of heterogeneous catalysis. Second one, it is that is intermediate compound formation theory. That is, second theory is intermediate compound formation theory. This is one more theory available for explaining catalysis, right? Okay, now apart from that, the third theory is what we call it as the modern adsorption theory of catalysis. Modern adsorption theory of catalysis. So these are the three theories that I can make use of in order to understand, yes, it is mechanism of, yes, it is heterogeneous catalysis. Let us see one by one. Adsorption theory. Now we can say this is the old theory. It's an old adsorption theory that I can use in order to explain heterogeneous catalysis. Heterogeneous catalysis, the physical states of reactants and catalysts will be different. During heterogeneous catalysis, the gaseous molecules or solute particles from solution are going to adsorb on the surface of catalyst. Thereby, concentration of reacting molecules on the surface of catalyst increases. And if the concentration of reacting molecules on the surface of catalyst increases, naturally rate of reaction increases. That is the concept of old adsorption theory. According to old adsorption theory, during heterogeneous catalysis, the gaseous molecules or solute particles from solution adsorb on the surface of catalyst, thereby concentration of reacting molecules on the surface of catalyst increases. That increases the rate of chemical reaction. At the same time, during adsorption, as you know that heat is liberated. That heat liberated during adsorption is utilized for increasing rate of chemical reaction. And that is what we call it as old adsorption theory of heterogeneous catalysis. And of course, as far as intermediate compound theory of intermediate compound formation theory is concerned, generally this intermediate compound theory is used to explain homogeneous catalysis. According to intermediate compound formation theory, during catalysis, reacting molecules react with catalyst to form unstable intermediate compound known as activated complex. You already studied this particular theory in reaction kinetics. According to intermediate compound formation theory, during catalysis, reacting molecules react with catalyst to form unstable intermediate compound known as activated complex. This intermediate compound decomposes to form products. So this is what we call it as intermediate compound formation theory. For example, if I consider reaction between A and B and okay, na? If this reaction is carried out in presence of catalyst C, you are going to get one intermediate, that is you are going to get one intermediate of this type. Yes, you are going to get one intermediate, that is A dot 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 C, C dot 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 P. This is intermediate compound. This intermediate compound is highly energetic. This intermediate compound is highly energetic, unstable, decomposes to form a product AB, along with the formation of catalyst. That is, during catalysis, catalyst will be regenerated. During catalysis, catalyst will be regenerated along with the product. So this is what we call it as intermediate compound theory. And as far as modern adsorption theory of heterogeneous catalysis is concerned, it will make use of both the concepts. It's a combination of old adsorption theory and intermediate compound formation theory. Let us see mechanism of heterogeneous catalysis according to modern adsorption theory. Okay, na? We'll see that. So let us see mechanism of heterogeneous catalysis based on the modern adsorption theory of catalysis, right? As far as the modern adsorption theory is concerned, the catalytic activity is localized on the surface of catalyst due to the presence of free valencies on the surface of catalyst. Okay, now that is according to modern adsorption theory of catalysis. The catalytic activity is localized. That means it will be concentrated on the surface of catalyst due to the presence of free valencies on the surface of catalyst. Now let us see different steps involved in the mechanism of heterogeneous catalysis according to modern adsorption theory. Okay, now we'll see one by one. Yes, as far as the first step is concerned, in heterogeneous catalysis, first step is diffusion of reacting molecules towards the surface of catalyst. That is the first step. That is the diffusion of reactants. Diffusion of reactants towards the surface of catalyst. This is the first step in heterogeneous catalysis. That is, during heterogeneous catalysis, reacting molecules are moving towards the surface of catalyst. That is the first step. And as far as in the second step is concerned, whatever the reacting molecules, they are moving towards the surface of catalyst, they get adsorbed on the surface of catalyst. That is the second step. That is, second step involves adsorption of reacting molecules, adsorption of reacting molecules on the surface of catalyst. That is adsorption of reacting molecules on the surface of catalyst. That is the second step involved in heterogeneous catalysis according to modern adsorption theory. There, the reacting molecules moving towards the surface of catalyst, they get adsorbed on the surface of catalyst. That is the second step. And as far as third step is concerned, these adsorbed reacting molecules on the surface of catalyst undergo chemical reaction through the formation of intermediate compound. That is, adsorbed molecules adsorbed reacting molecules, adsorbed reacting molecules अथवा adsorbed reactants undergo chemical reaction through the formation of intermediate compound, that is through the formation of intermediate compound. That is the third step involved in heterogeneous catalysis according to modern adsorption theory. The reacting molecules adsorbed on the surface of catalyst get reacted through the formation of intermediate compound. And of course, as far as the intermediate compound is concerned, this intermediate compound is unstable, undergo decomposition to form products. That is, this intermediate compound formed on the surface of catalyst is unstable, undergo decomposition to form a product on the surface of catalyst. And of course, in the fourth step, the products formed on the surface of catalyst have less affinity for the surface of catalyst. Therefore, the products formed during chemical reaction get dissolved from the surface of catalyst. That is the fourth step. That is, the products of reaction dissolved. Products of reaction dissolved from the surface of catalyst. So that new surface is made available for fresh reacting molecules. That is, the products of reaction dissolved from the surface of catalyst, so that a new surface is made available for the adsorption of fresh reacting molecules. So that is what we call it as fourth step. In the fifth step, the products of reaction get diffused away from the surface of catalyst. That is the fifth step. That is, in the fifth step, the products formed in a chemical reaction diffused away from the surface of catalyst. That is the fifth step. That is diffusion of products of reaction. Away from surface of catalyst. These are the 5 steps involved in the mechanism of heterogeneous catalysis as far as modern adsorption theory of catalysis is concerned. As far as the modern adsorption theory is concerned, these are the 5 steps involved in the mechanism of heterogeneous catalysis. First step is diffusion of reacting molecules towards the surface of catalyst, and then they are going to adsorb on the surface of catalyst. That is, adsorption of reacting molecules on the surface of catalyst due to the presence of free valencies. These adsorbed reacting molecules undergo chemical reaction on the surface of catalyst through the formation of intermediate compound. That intermediate compound is unstable, undergo decomposition to form products, and these products formed on the surface of catalyst get dissolved from the surface of catalyst, so that new surface is made available for fresh reacting molecules. And of course, as far as fifth step is concerned, these products formed during catalysis diffused away from the surface of catalyst. So this is what we call it as 5 steps involved in the mechanism of heterogeneous catalysis according to modern adsorption theory of catalysis. We'll see the schematic diagram involved in the mechanism of heterogeneous catalysis according to modern adsorption theory. We'll see that. Yes. Look here, this is a schematic diagram that I can use in order to explain heterogeneous catalysis or modern adsorption theory of heterogeneous catalysis. Okay, now look at this. This is a catalyst. Look at this. These are the particles of catalyst. And just observe, the surface of catalyst will be characterized by unsatisfied valencies, or you can say free valencies. When this catalyst come in contact with reacting molecules, these reacting molecules will be adsorbed over the surface of catalyst. Observe here, A and B are the reacting molecules. They are going to adsorb. They are going to be attached to the surface of catalyst. A is attached to this, B is attached to this. That is, A and B reacting molecules undergo adsorption over the surface of catalyst. Is it not? And these adsorbed reacting molecules undergo chemical reaction to form intermediate compound. Just observe here, I am not showing any bond between A and B. Here, A and B molecules are just adsorbed on the surface of catalyst, and once the adsorption of reacting molecules takes place, these adsorbed reacting molecules undergo chemical reaction to form intermediate compound. this intermediate compound is unstable, undergo decomposition to form products, and these products formed on the surface of catalyst undergo desorption that results in the formation of that results in the regeneration of catalyst used in this particular reaction. And of course here it is a AB, that is product of this particular reaction, and of course this is a catalyst that is regenerated during a chemical reaction. Look at this. As far as modern adsorption theory of heterogeneous catalysis is concerned, the catalyst is characterized by free valencies, or you can say that unsatisfied valencies. Now, these unsatisfied valencies on the surface of catalyst provide seat for chemical forces for attraction. When such type of catalysts, when they are exposed to the reacting molecules, the gaseous reacting molecules will be attached to the surface of catalyst through loose chemical combination. And because of that, if more and more reacting molecules are adsorbed on the surface of catalyst side by side, they may undergo chemical reaction to form products. These products formed on the surface of catalyst undergo desorption, so that a new surface is made available for the adsorption of fresh reacting molecules. So this is what we call it as the modern adsorption theory of heterogeneous catalysis. And of course, as the surface area of catalyst increases, the catalytic activity increases. As the surface area of catalyst increases, catalytic activity increases. And so that is in finely divided state, the surface area of the substance will be relatively more compared to that in bulk state. Now, in finely divided state, the surface area of the substance will be more compared to that in bulk state. Because of that, we are going to use catalyst, in finely divided form. So this is what we call it as the modern adsorption theory of heterogeneous catalysis. And of course, as far as modern adsorption theory of heterogeneous catalysis is concerned, this modern theory of heterogeneous catalysis successfully explained why the catalyst remains unchanged in its composition and mass at the end of the chemical reaction. As far as the limitation of this particular modern adsorption theory of heterogeneous catalysis is concerned, this theory could not explain the effect of catalytic poisons and catalytic promoters on the activity of catalysts. So this is what we call it as the modern adsorption theory of heterogeneous catalysis. Now at this moment, according to your NCERT textbook, I supposed to discuss important features of solid catalysis, right? Now let us see, that is important features of solid catalyst. Okay, let us see that next discussion under catalysis is important features of solid catalyst. And of course, here under this particular headline, we are going to determine efficiency of the catalyst by using certain properties of catalyst, that is activity and selectivity. These are the two important features as far as solid catalysts are concerned. We'll see one by one. So it is as far as activity of catalyst is concerned. Activity of catalyst refers to the ability of a catalyst to accelerate the rate of chemical reaction. The ability of catalyst to accelerate rate of chemical reaction is called activity of catalyst. As far as the catalysts are concerned, catalyst is characterized by free valencies on its surface. Just to remember what we discussed under the mechanism of heterogeneous catalysis. The surface of catalyst is characterized by free valencies. Because of that, catalyst adsorb reacting molecules on its surface through loose chemical combinations. Catalyst is going to adsorb reacting molecules on its surface through loose chemical combinations. That means when catalyst is exposed to the reacting molecules are attached to the surface of catalyst through chemical bonds. That is, the reacting molecules attached to the surface of catalyst through chemisoption. Reacting molecules are attached to the surface of catalyst through chemisoption. And here the activity of catalyst depends on strength of chemisoption. The activity of catalyst depends on strength of chemisoption between reactants and catalyst. Okay, strength of chemisoption between reactants and catalyst. That is, the activity of catalyst depends on the strength of chemical bond between catalyst and reacting molecules. It should not be too strong and too weak. The strength of chemical bond between catalyst and reactants should not be too strong and too weak. It should be moderately strong. It should be moderately strong. So, the activity of catalyst depends on the strength of chemical bond between catalyst and reacting molecules. And the strength of chemical bond should not be too strong and too weak. It should be moderately strong so that adsorbed reacting molecules get reacted and the products formed in a chemical reaction should leave the surface as soon as they are formed. Then only the catalytic activity will be maximum. If the strength of bond between reactants and catalysts is too strong, if the strength of bond between catalysts and reactants is too strong, the reacting molecules get immobilized and the products of the reactions do not leave the surface as soon as they are formed, then the other reacting molecules do not get a fresh surface for adsorption. Thereby, the catalysts become inactive. Because of that, the strength of chemical bond between reactants and catalysts during catalysis should be moderately strong. Should be moderately strong. It should not be too strong and too weak. And because of that, what we can say at this moment, that catalyst should adsorb reacting molecules fairly strongly, but not so strongly that the reacting molecules get immobilized and no surface is left for other reactants to adsorb. And that is what we call it as activity of catalyst. Okay, now in order to justify the activity of catalyst, I go for one example, that is reaction between hydrogen and oxygen, right? When hydrogen gas is mixed with oxygen gas, and of course no chemical reaction takes place. When hydrogen gas mixed with oxygen gas, no chemical reaction takes place. If these two gases are mixed in presence of finely divided platinum catalyst, if these two gases, they are mixed in presence of finely divided platinum catalyst, the chemical reaction is highly violent, or you can say the chemical reaction is highly explosive, and that results in the formation of water. That's why, the activity of catalyst can be justified by using this particular example. At the same time, as far as the activity of catalyst is concerned, with respect to the reaction, hydrogenation of oils. With respect to the reaction, hydrogenation of oils, the catalytic activity of transition metals increases from 5th group to 11th group in the periodic table. And of course, it has been found that, catalytic activity of transition metals will be maximum for the elements belonging to 7th group to the, yes, it is 7th group to the, yes, it is 9th group. The elements belonging to 7th group to 9th group of the periodic table will show maximum catalytic activity with respect to the hydrogenation of oils. Because of that, hydrogenation of oils will be carried out by using elements belonging to the 7th group to the 9th group. Okay, now, so this is what we call it as the activity of catalyst with respect to the features, important features of solid catalyst. We'll see next important feature of solid catalyst. It will be, yes, it is selectivity there. Okay, now we'll see selectivity now. Yes. As far as one more feature of solid catalyst is concerned, it will be selectivity there. That is another feature of solid catalyst. Selectivity, one of the important features of solid catalyst, that refers to the ability of catalyst to direct a chemical reaction to yield a particular product. The ability of catalyst to direct a chemical reaction to yield particular product, and that is called as selectivity. That means, catalyst has got that ability of deciding the nature of the products formed in a particular chemical reaction. Or you can say the products formed in a chemical reactions will be decided by the type of catalyst used in that particular chemical reaction. And of course, it has been observed that, for a given reacting molecules, if I use different catalysts, different products will be formed. And of course, for example, if I take the reacting molecules or reaction between hydrogen and carbon monoxide. Just observe the reaction between hydrogen and carbon monoxide gases. If I carry out the reaction between hydrogen gas and carbon monoxide gas in presence of a catalyst nickel, if I carry out reaction between hydrogen and carbon monoxide in presence of a catalyst nickel, you are going to get methane gas along with the formation of water. Here, the products of this reaction will be methane and water in presence of nickel catalyst. And of course, in order to balance it, here we have one oxygen atom. Therefore, it will be H2O. 6 hydrogen atoms are there. Therefore, it should be 3H2. So this is balanced equation. For this particular reaction, if I use nickel catalyst, the products of the reaction will be methane and water. If same reacting molecules are allowed to undergo chemical reaction in presence of one more catalyst, that is by using copper in presence of zinc oxide and chromium oxide. If these two gases are allowed to react by using copper in presence of zinc oxide and chromium oxide, ZnO, Cr2O3, the product of the reaction will be, look at this, CS3OH. The product of the reaction will be CS3OH. Look at this, you are going to get methanol. Just observe these two reactions. The type of reacting molecules will be same, but type of catalyst will be different. As the nature of catalyst changes, nature of products will be changed. That's why I said the catalyst has got that ability of directing a chemical reaction to yield a particular product, and that is what we call it as selectivity. And at the same time, in order to balance this, we go for 2H2 here. If these two gases are allowed to react, in presence of copper catalyst, observe the product will be formaldehyde, that is HCHO there. Like that, just observe, as the nature of catalyst changes, nature of products formed in a chemical reaction will change. That's why that catalyst has got that ability of directing a chemical reaction to yield a particular product. And at the same time, as far as catalysts are concerned, a catalyst cannot catalyze more than one chemical reaction. A substance that is used as a catalyst in one particular reaction cannot catalyze all other reactions. That is what we call it as selectivity there. So this is what we call it as one more important feature as far as solid catalyst is concerned. And that's why I said the efficiency of catalysis can be decided on the basis of activity and selectivity of solid catalyst. So that is what we call it as important features of solid catalyst. Now at this moment, we'll go to the one more important topic, what we call it as shape selective catalyst. We'll see that shape selective catalysis. That is the next discussion as far as the topic catalysis is concerned. Look at this, a shape selective catalyst. Shape selective catalysis. And especially as far as shape selective catalysis is concerned, generally we make use of zeolites. We make use of zeolites as shape selective catalyst. Look at this, what exactly this shape selective catalyst stands for. The catalytic reaction which depends on pore structure of catalyst and size of the reactant and product molecules, that is called as shape selective catalysis. The catalytic reaction that depends on the pore structure of catalyst and size of reactant and product molecules is called shape selective catalysis. And of course, what is that pore structure of catalyst? I'm using the term here, pore structure of catalyst. As far as zeolites are concerned, zeolites are the catalyst which will be characterized by, yes, it is the pores on their surface, or you can say that cavities on their surface. Generally, zeolites are used as shape selective catalysts because these zeolites are characterized by honeycomb-like structure. Zeolites are characterized by, yes, it is honeycomb-like structure. That is, the structure of zeolites will be almost similar to the structure of honeycomb. Honeycomb is characterized by cavities and pores on its surface. Just like that, zeolites are characterized by various cavities and pores on their surfaces. Because of that, zeolites are said to be having honeycomb-like structure. Due to the presence of these honeycomb-like structures, zeolites act as shape selective catalysts. As far as the chemical nature of zeolites is concerned, chemically, zeolites are aluminosilicates. Chemically, zeolites are aluminosilicates with three-dimensional network of silicates. Three-dimensional network of silicates in which some of the silicon atoms are replaced by aluminum atoms to give ALOSI framework. This is what we call it as the chemical nature of zeolites. Zeolites are aluminosilicates with a three-dimensional network of silicates in which some of the silicon atoms are replaced by aluminum atoms to give ALOSI framework. That is, if you observe the structure of aluminosilicates, the structure of aluminosilicates is characterized by network of ALOSI bonds. The structure of aluminosilicates is characterized by the network of ALOSI bonds. And because of that, we'll find various cavities and pores on the surface of acetic catalyst. The catalytic activity of zeolites depend on the size and shape of the pores and cavities on the surface of zeolites and also size and shape of the reactant and product molecules. For example, imagine if a zeolite is characterized by cavities on its surface like this. Yes. Imagine a zeolite. The surface is characterized by cavities like this. Yes. The surface of zeolite will be like this. The cavities are like this. Yes. These are the cavities on the surface of zeolites. Yes. Look at the size and shape of the the cavities of the zeolites on the surface of zeolites. Just imagine if the reacting molecule is too small, if it is small enough to enter into the cavities of zeolites, then only zeolites can bring about catalysis of a reaction. At the same time, the products formed during catalysis should leave the products formed during catalysis should leave the cavities as soon as they are formed. Then only zeolite can act like a catalyst. If look at this, imagine this is one molecule. Its shape is like this. Look at the shape of the cavities. It is a square, but the shape of the molecule is like pentagon. This particular molecule, which is bigger than the size of the cavities of zeolites, it will not enter into the cavities of zeolites. At the same time, the shape of the reacting molecule is different from the shape of the cavities of zeolites. In such cases, zeolites do not adsorb the reacting molecules which are too big to enter into the cavities of zeolites. That's why I said, the catalytic activity of zeolites depends on size and shape of the pores and cavities on their surfaces. At the same time, size and shape of the reactant and product molecules. That is, a zeolite can adsorb those reacting molecules which are small enough to enter into the cavities of zeolites. At the same time, products formed in a chemical reaction should leave the surface as soon as they are formed. If the size of the reacting molecules is too big, then zeolite will not adsorb those reacting molecules and it will not bring about catalysis of those reacting molecules. And that is what we call it as shape selective catalyst. That means, these zeolites act like a sieve. These zeolites act like a sieve. Sieve. A sieve is a device that is used to bring about separation of smaller particles from bigger particles. That is what we call it as sieve. Here also, zeolites act like a sieve. And of course, as far as zeolites are concerned, they got their own importance in industries. They got their own importance in various industries, especially in petrochemical industries. Zeolites used as a catalyst to bring about cracking of hydrocarbons and isomerization of hydrocarbons. In cracking of hydrocarbons, higher hydrocarbons will be converted into smaller hydrocarbons. In isomerization reactions, one isomer will be converted into another isomer. That is, in order to bring about catalysis of cracking of higher hydrocarbons and isomerization of hydrocarbons, we make use of zeolites. At the same time, I'll give one example, that is ZSM5. This is one zeolite. ZSM5 is one zeolite. It acts as a catalyst in conversion of alcohols into gasoline. That is, this ZSM5 is used as a catalyst in the conversion of alcohols into petrol. Here in this reaction, ZSM5 will bring about dehydration of alcohols into mixture of hydrocarbons, and that is nothing but petrol there. So this is what we call it as the ZSM5, one of the examples for shape selective catalyst. That is, shape selective catalysis is the catalytic reaction which depends on the pore structure of catalyst and size and shape of the reactant and product molecules. So this is what we call it as shape selective catalysis, and application of shape selective catalysis in various industries. Now at this moment, as far as your NCERT textbook is concerned, we are supposed to discuss what we call it as enzyme catalysis. Let us see enzyme catalysis. This is one more discussion. You are very much familiar with certain biomolecules called enzymes. Enzymes are complex nitrogenous organic compounds which act as a catalyst in various biochemical reactions. So we call them as enzymes. Or you can say enzymes are proteins which will act as a catalyst in various biochemical reactions. We call them as enzymes. Of course, as far as enzymes are concerned, these enzymes act as catalysts in various biochemical reactions occurring in the bodies of plants and animals. Because of that, these enzymes are called as biochemical catalysts, and the phenomenon is called as biochemical catalysis. And of course, as far as enzyme catalysis is concerned, I'll give some examples for the enzyme catalysis. Okay, now we'll see one by one. First of all, yes, in the hydrolysis of sucrose, look at the C12, H22, O11. This is sucrose. It undergoes hydrolysis, right? In presence of enzyme called invertase. Invertase is enzyme that brings about hydrolysis of sucrose into glucose and fructose. That is C6H12O6 plus C6H12O6. This is hydrolysis of sucrose into glucose and fructose in presence of enzyme called invertase. The source of invertase in this particular catalysis is what we call it as yeast cells. Yeast cells are the source of invertase enzyme which will bring about, yes, it is catalysis of hydrolysis of, yes, it is sucrose into glucose and fructose. This is one example for the, yes, it is enzyme catalysis. Here, invertase is used as a catalyst. Just observe, as far as names of the enzymes are concerned, generally, in most of the cases, names of the enzyme end with ASE. Okay, now? Look at this hydrolysis of starch here. Hydrolysis of starch. This is a starch, N times. So polymer of glucose molecules, is it not? That is starch undergoes hydrolysis with N number of water molecules, right? In presence of enzyme called diastase to form, yes, it is N number of, yes, it is maltose molecules. This is what we call it as maltose. The conversion of starch into maltose is brought about by the enzyme called diastase. The source of this diastase is malt, that is. Malt itself is a source of diastase as far as the enzyme diastase is concerned. As far as third example is concerned, look at this. This C12, H22O11, one of the disaccharides called maltose, yes. And maltose undergoes hydrolysis in presence of enzyme called maltase. And maltose undergoes hydrolysis in presence of enzyme called maltase that leads to the formation of two molecules of glucose, C6H12O6. And maltose, C12H22O11 undergoes hydrolysis that leads to the formation of two molecules of, yes, it is glucose there. And of course, your maltase is an enzyme. The source of maltase is, once again, yeast cells. And as far as fourth example is concerned, that is hydrolysis of urea there. One more example for the enzyme catalysis, hydrolysis of urea. Urea undergoes hydrolysis in presence of enzyme called urease. Urea undergoes hydrolysis in presence of enzyme called urease that leads to the formation of ammonia. That leads to the formation of ammonia and of course carbon dioxide there. Look at this 2NSA and carbon dioxide. That is hydrolysis of urea into ammonia is brought about in presence of enzyme called urease. And the source of urease is soybean. Soybean is the source of urease. As far as the fifth example is concerned, that is the conversion of glucose, C6H12O6, conversion of glucose into ethyl alcohol, conversion of glucose into ethyl alcohol, C2H5OH plus carbon dioxide. This particular conversion of glucose into ethyl alcohol is brought about by one more enzyme called zymase. One more enzyme called zymase. Once again, the source of zymase is yeast cells. Observe, here we have 6 carbon atoms, therefore it is 2 C2H5OH and of course 2 CO2 molecules, so the total 6 carbon atoms. And as far as 6th example is concerned, that is conversion of proteins into peptides is brought about by the enzyme present in the stomach called, this is pepsin. Pepsin is one enzyme present in the stomach that brings about hydrolysis of proteins into peptides, and the source of pepsin is stomach itself. At the same time, proteins can be converted into amino acids, that is, proteins can be converted into amino acids by the hydrolysis of proteins in presence of pancreatic trypsin. That is, trypsin is one more enzyme that brings about hydrolysis of proteins into amino acids. This trypsin is present in intestine. Pancreatic trypsin is present in intestine. Apart from that, conversion of milk into curd is brought about by one more enzyme that is called as lactobacilli there. That is conversion of, yes, it is milk into curd is brought about by one more enzyme called lactobacilli present in curd. So these are some examples for enzyme catalysis. Hagadre, as far as enzymes are concerned, they are the complex nitrogenous organic compounds which act as catalysts in various biochemical reactions. So we call them as enzymes. Hagadre, enzymes are the proteins which will catalyze various biochemical reactions. That is what we call it as enzymes. Agwadala. Now at this moment, according to your NCERT textbook, we are supposed to discuss the properties of enzyme catalysis. Agwadala, we'll see that. Yes. Properties of enzyme catalysis. This is one more discussion as far as your NCERT textbook is concerned under catalysis. As far as first property of enzyme catalysis, that is enzymes are highly efficient. Enzymes are highly efficient in their action. That is, enzymes are highly efficient in increasing rate of chemical reactions. In order to justify that efficiency of enzyme catalysis, I'll give an example. That is, one molecule of enzyme can bring about transformation of million reacting molecules into products in 1 minute. Okay, now that is the first property. Second property, enzymes are highly specific. And of course, the activity of catalyst itself is a specific in nature. That is highly specific in their action. Just like, the activity of catalyst will be specific. Even catalysts are also specific in nature. That is, particular reaction is catalyzed by particular type of catalyst. Like that, particular enzyme cannot bring about catalysis of more than one biochemical reaction. One particular biochemical reaction is catalyzed by one particular enzyme only. That's why, enzymes are highly specific. For example, that is hydrolysis of urea into ammonia is brought about by the enzyme called urease. And that urease cannot bring about hydrolysis of other amides. That urease can bring about hydrolysis of only urea into ammonia. That same urease cannot be used as a catalyst to bring about hydrolysis of other amides. Urea is an amide. Like that, same urease cannot be used to bring about catalysis of other amides. So this is what we call it as the nature of enzymes. Enzymes are highly specific in their action. The third property, that is with respect to the optimum temperature. Enzymes are characterized by optimum temperature. That is catalytic activity of enzymes will be very, very high at one particular temperature called optimum temperature. That is, optimum temperature is the temperature at which the rate of enzyme catalyzed reaction will be highest, and that particular temperature is called as optimum temperature. At that particular temperature, the catalytic activity of enzyme will be very, very high. Generally, optimum temperature range will be from 298 kelvins to 310 kelvins. This is the optimum temperature range. And of course, if the temperature of biochemical reaction is less than 298 kelvins, then catalytic activity of enzymes will be less. At the same time, if the temperature of biochemical reaction is more than 310 kelvins, then the catalytic activity of enzymes will be less. Because of that, what I can say at this moment, that is the catalytic activity of enzymes will be less on either side of this optimum temperature. And of course, the body temperature of human beings will be, is generally, 310 kelvins. So the human body temperature will be 310 kelvins. It is very much suitable for enzyme catalysis. At this particular temperature, the catalytic activity of enzymes will be very, very high. So this is what we call it as the optimum temperature. At the same time, enzymes are characterized by optimum pH. At the same time, enzymes are characterized by optimum pH. That is, the optimum pH refers to the pH value of biochemical reaction at which the rate of enzyme catalysis reaction will be very, very high. Or you can say the pH of biochemical reaction at which the catalytic activity of enzymes will be very, very high. That is what we call it as optimum pH. Generally, the catalytic activity of enzymes will be very, very high at a pH range of 5 to 7. So this is what we call it as optimum pH range for enzymes. So this is the fourth property as far as enzymes are concerned. As far as fifth property is concerned, that is influence of coenzymes. Influence of coenzymes and activators. Coenzymes are non-protein molecules in presence of which the catalytic activity of enzymes will be maximum. And such type of non-protein molecules which will increase the catalytic activity of enzymes, they are called as coenzymes. At the same time, we have certain metal ions like Na plus ions, Cu2 plus ions, Mn2 plus ions, CO2 plus ions, etc. These are the some metal ions. In presence of these metal ions, the activity of enzymes will be, the catalytic activity of enzymes will be maximum. In presence of these metal ions, the catalytic activity of enzymes will be maximum. That's why, these metal ions are called as activators. These activators will be attached to the surface of enzymes through weak chemical bonds. Thereby, catalytic activity of enzyme increases. For example, in presence of Na plus ions, activity of amylase enzyme increases, right? And of course, that is one more property as far as the properties of enzymes are concerned. And of course, with respect to the sixth property, influence of inhibitors, or you can say that poisons. Influence of inhibitors or poisons, right? Now, as far as enzymes are concerned, the catalytic activity of enzymes can be decreased in presence of certain chemical substances called poisons or inhibitors. Generally, heavy metal atoms like mercury and silver can act like, that is, poisons for enzymes. In presence of catalytic poisons, the activity of catalyst will be completely destroyed, because these inhibitors, they are going to interact with active functional groups present on the surface of enzymes. These inhibitors, they are going to interact with active functional groups present on the surface of enzymes. Thereby, the catalytic activity of enzymes will be destroyed. So that is what we call it as, in presence of inhibitors and, or you can say, poisons, the catalytic activity of enzymes will be decreased. This is what we call it as sixth property as far as enzymes are concerned. So okay, so these are the some properties as far as the enzyme catalysis is concerned. Okay, in the next video, we'll see one more discussion under enzyme catalysis. It will be mechanism of enzyme catalysis. Okay, after that, we'll start one more topic under surface chemistry. It will be colloids. We'll see that in the next video. Thank you very much. Yes.